In Module 2.3, we will discuss precipitation. To understand how climate change will impact precipitation, we first need to look at the water cycle. This is a simplified graphic of the water cycle that you may be familiar with, but we will review it together. So starting in the clouds at number 3, water exists in the atmosphere as water vapor, which is the gas form of water. When it's in the atmosphere, water will cool and condense to its liquid form and be released, falling to the surface of the earth as precipitation or rainfall. Once it reaches the surface, it is transported as surface runoff, making its way to our rivers, our lakes, and our streams, and it also gets soaked up by the ground. Once it is in the bodies of water, it will evaporate, as you can see in number 2 here. And if water is soaked up in the ground, it will evaporate through a process called transpiration from plants and vegetation, as you can see by the number 1 here. Once it evaporates and gets back into the atmosphere as water vapor, it will condense back into its liquid form, and the cycle will repeat again. Increasing temperatures will impact the water cycle by increasing evaporation of water from land and bodies of water. Additionally, as the Earth warms up, glaciers and ice sheets will melt, adding more water to the oceans and overall to the water cycle. This can result in changes to normal precipitation patterns related to the amount, timing, and distribution of precipitation. So we could see more frequent and intense heavy precipitation events where a lot of rain falls at one time. We could also see changes to seasonal precipitation, so for example, an increase or decrease in certain months. Finally, we could see a change in the overall total precipitation. Some regions may experience an increase, while others may experience a decrease. With climate change, we often describe this as wet areas will get wetter and dry areas will get drier. This can also mean wet seasons will get wetter and dry seasons will be drier. How has global land precipitation, so that's precipitation that falls on land, how has that changed over time? This graph is showing global land precipitation anomalies relative to 1981 to 2010 baseline, and it's from the IPCC 6th Assessment Report. It may look a little complicated, but I'll explain it and we'll go through it together. So what scientists did is they took the global land precipitation in millimeters per year for every year between 1891 all the way to 2019. So they took the land precipitation for all of those years and they compared it to a baseline period. So they compared it to the average precipitation for 1981 to 2010. The difference between each year and the baseline period is known as the anomaly. So if a point on the graph is above the 0 line, so anywhere in this range, it means that precipitation for that year was higher than the baseline period. If a point on the graph is below the 0 line, so anything in this range, it means precipitation for that year was lower than the baseline period. You may notice there are 3 different colors or 3 different lines on this graph, and each line is representing a different global precipitation data set. And the data sets are here, but don't need to really worry about that. You can notice, based on this graph and the different trend lines, that there is a slightly positive, meaning the precipitation anomalies are above 0, so slightly positive trend in the precipitation anomalies. And we can see that the trend in positive precipitation anomalies occurs in the 1950s, so around here, 1970s, so kind of around here. You see a big positive in this year. And then we also see a positive from 2000 to 2019. So all of these values, for the most part, are in the positive range, meaning that overall, global land precipitation has likely increased since about the 1950s, and we've observed a faster increase in precipitation since the 1980s. What does current precipitation look like in Suriname? Again, I will present sort of the current characteristics of precipitation, and then we'll discuss how precipitation has changed over the 1990 to 2014 time period. So in terms of accumulated yearly precipitation, it is just over 1,500 millimeters for all of Suriname. However, precipitation varies depending on the region and the season. The southwest region usually receives more than 3,000 millimeters per year, and the coastal region receives more than 2,500 millimeters per year. Most of the rain falls during the wet season. Over the 1990 to 2014 time period, we see a strong increasing trend in accumulated yearly precipitation. Let's look at this further in graph and data form. Let's look at some maps and data of the current precipitation in Suriname from the 2021 State of Climate Report. So this figure is showing average accumulated yearly precipitation in millimeters per year for the period 1990 to 2014. As we can see, the average accumulated precipitation varies across Suriname. The southwest experiences the most yearly precipitation, about 3,500 millimeters per year, and the coastal region experiences about 2,500 millimeters per year. The four figures on the right are showing the average accumulated precipitation in millimeters for the dry season, the rainy season, the short dry season, and the short rainy season, again for 1990 to 2014. As we can see in all of these figures, there is a large difference in precipitation based on where you are in Suriname and based on the season. The main driver of this difference has to do with the proximity to sea, the elevation, and the annual cycle of the Intertropical Convergence Zone, or the ITC zone. This zone is an area near the equator between the northern and southern hemisphere, where the northeast and the southeast trade winds meet. The ITC zone moves throughout the year, and this affects rainfall and determines wet and dry seasons in the tropics. This table illustrates the trends in regional precipitation, again over the 1990 to 2014 time period that we discussed in previous slides. Again, we can see the average value of precipitation in millimeters per year and the rate of change per decade. So as we can see in this table, precipitation shows a strong increasing trend in all 7 points of interest, including an increase of up to 546.6 millimeters per decade in Kwamala-Samutu. What about extreme precipitation? This first map is showing the average number of yearly rain days between 1990 to 2014. We can see based on the yellow and orange colors, the range of yearly rain days is somewhere between 200 to just over 250. Rainy days are slightly more frequent on the coast, the center, and in the southwest region of the country, and less so on higher ground towards the southeast. Suriname tends to experience a high number of rainy days. The map on the right is showing the maximum daily precipitation in millimeters per day. So when Suriname experiences a heavy precipitation event, the maximum value of precipitation for a single day lies somewhere around the 110 millimeter range. We can see the maximum value in daily precipitation is higher slightly in the center and in the southwest of the country, as can be seen by the darker blue and even purple colors here. What will precipitation in Suriname look like in the future? The State of Climate Report assessed two emission scenarios. So recall SSP 2 4.5, the middle or intermediate emission scenario, and SSP 5 8.5, high emission scenario. They looked at the reference period 1990 to 2014 and compared it to 3 future time periods. So what can we expect in terms of precipitation? average accumulated precipitation in Suriname is expected to decrease strongly for both scenarios over all time periods. This decrease will be more pronounced in the southwest region and on the coast. The reason for this projected decrease is that the average position of the intertropical convergence zone is expected to gradually shift northwards as the northern hemisphere warms faster than the southern hemisphere. In terms of extreme precipitation, Suriname can expect a decrease in the number of rainy days, particularly in the long term and in the coastal region. Extreme precipitation events are projected to increase. This, together with the decrease in the number of rainy days, point to a change of the precipitation regime towards fewer but more intense events. These maps are showing average accumulated precipitation under the SSP2 4.5 scenario for 3 different future time periods, as you can see. We can see the maximum values of up to 3,500 millimeters per year of precipitation in the southwest gradually reduces, so there's less average precipitation. It could be reduced by up to 500 millimeters per year by the end of the century. We can also see this trend on the map as the red and pink colors slowly begin to disappear on the southwest as time goes on. These maps are showing the average accumulated precipitation again, but for the SSP5 8.5, which is the high emission scenario. Again, we are looking at 3 different future time periods, as we can see. So for SSP5 8.5, the maximum values of 3,500 millimeters per year of precipitation could decrease by 900 millimeters per year, for a maximum accumulated precipitation of about 2,600 millimeters per year in the southwest. The projected decrease of precipitation is also very strong in the coast, which points to a decreasing trend from 2,500 to 2,000 millimeters per year. And again, you can see this change based on how the red and pink colors slowly fade as time goes on in the southwest as well as on the coast. Where will we see the largest amount or magnitude of change in average accumulated precipitation? These maps are showing the average accumulated precipitation anomaly. So similar to temperature anomaly, the scientists take the average accumulated precipitation for the reference period, in this case 1990 to 2014. So they take that average and they compare it to the future time period average. So in this case, we're looking at 2070 to 2094. And the difference in those 2 averages is known as the anomaly. So the map on the right is showing on the left is showing SSP2 4.5, and the map on the right is showing SSP5 8.5, both for the long-term projection, so the end of the 21st century. We can see the projected decrease in precipitation is the strongest in the southwest region as well as the coastal region, and this is for both SSP2 4.5 and SSP5 8.5. But for the higher emission scenario, the decrease is strongest, and we can tell by these dark blue colors here. What about future extreme precipitation? The number of rainy days is projected to decrease, meaning Suriname will have more dry days where there's no precipitation. This is most evident in the long term and for the coast, but it can also be observed in the interior in the short and long term. So both Paramaribo and Albina will suffer the largest decrease of more than 15% in the number of rainy days by the end of the century, and this is more pronounced for the SSP5 8.5. So if you pause the video and look at the values, you can see they are strongly decreasing for SSP5 8.5 as time goes on. Other regions, such as Kwamalasemutu, will experience a small decrease, only about 5% in the number of rainy days by the end of the century. Maximum one-day precipitation is projected to increase greatly for all locations, especially for maximum precipitation in 5 days. This, together with the decrease in number of rainy days, points to a change of the precipitation regime towards fewer but more intense precipitation events in Suriname.